this, so that's going to be pretty lit. Happy about that. Was worried we'd have to talk about machine learning all by ourselves in here. I'm kind of wondering, while people sort of trickle in, if people could just raise their hands if anyone's had any experience actually implementing any sort of machine learning algorithms, or you have cool, or someone's who's just like new to it, they're interested in it, they're maybe wondering what it's all about. Is anybody like that? I've been that person, so cool, okay. And then how many people here are interested in maybe getting some machine learning magic going in their games or whatever? I guess probably games, cool, okay. Just getting a gauge. This is gonna be a very, I think I might have put in the description, a very gentle introduction. So I wanted to make sure that was on a good level, because we can go more in depth, but that's confusing, so we won't do that today. Okay, cool, just wondering. Awesome, so hopefully we're all in the right room, which is this. We're gonna learn how to learn today, be a little bit meta. And this is specifically about enhancing educational games with machine learning. How many people in here are interested in educational games? Okay, great, okay. This can definitely apply to non-educational games, but that's kind of the focus of the talk, but okay, cool, I was just curious. All right, so as a brief introduction to me, I'm Katie, hello, nice to meet you. This work that we're gonna be talking about here is a little bit, a bit based on my master's thesis that I did, machine learning and modifying games using different machine learning techniques. So that's a bit about me. I'm also in an indie game studio. We just released our first game, woo, this past December, so we'll have some shameless plugs at the end, but that's a bit about my background. Other sort of notable things in my background is my undergraduate degree is actually not in computer science. My undergraduate degree is in adolescent English education. Any education majors here? Oh, nice, okay. Representing. So I got my undergraduate degree in English education, then I got my master's in computer science. Now I'm a full-time software engineer moonlighting as a professional person who draws pictures for you all. So, cool. All right, so we're gonna go ahead and get started. So we're going to sort of base this talk around this big, interesting question of how can we make educational games, or really any game, challenging and fun for each unique player. So this is obviously something that anyone who makes games is gonna be interested in. Answering this question, because you want games that are fun and also challenging, especially with educational games. Educational games that might be fun might not actually be useful. So like I could play type to learn, but I already know how to type, so that might be fun, but I wouldn't be learning anything. So that's kind of the question that we're going to be looking at today, and that question of course is two parts, which is what does it mean for a game to be challenging, and then what does it mean for a game to be fun? And there's obviously, I could have a whole talk about that, but I'm gonna just sort of boil it down to this potentially very boring looking math. So there's this concept called the Yerkes-Dodson law, and optimal stress levels, which again sounds super exciting. So basically, they've done a lot of research about a lot of different things, but the thing that I was reading about that I was particularly interested in is their research basically says that tasks that you do require some varied level of like arousal or stimulus in order to induce an optimal performance. So basically, there's some optimal level of arousal that will elicit the highest level of performance. This is not just in games, this is just in general. But I read a lot about this. I think I found out about this study in particular when I was in my undergrad, and I thought it was really cool. So I drew a helpful graph. As you can see, the bottom is level of arousal. So low is hopefully not this talk, but maybe it is, and high is you're on a roller coaster going 95. Like, woo, we're really like going really hard. And then for performance, weak performance would be, you know, you're not doing very good at the task, and then a strong performance would be you're doing really well. So you can sort of see if the level of arousal is too low, you're probably not going to do very well because you're bored. And if it's really high, you're not going to do very well because it's too much. So that might make sense now why I put on this slide, which is basically games that are both challenging or fun. We won't want games that are too easy, that's not challenging, and we don't want games that are too hard, because that's not fun, which obviously is very intuitive, but That graph that we see is going to be helpful for us in a little bit. So basically, the question that we're going to be answering is, how can we make games that are just right? So we want to reach that sort of optimal peak in the middle, where the level of arousal is at that point where we're getting a high level of performance. So we're not bored, but we're also not too challenged. So that's what we're going to be trying to figure out how to do today. Those of us in the gaming community might know that a common approach to this is basically some version of a bucket. So we say, okay, people have different, I guess there's one thing I should mention, which is this curve is going to look different for different people. So different levels of arousal need to exist for different people, for different tasks, different times. This curve is going to be different every time a player plays a game and what game it is. Should have mentioned that. So anyway, so the common approach to this that we use a lot in game design is some form of a bucket. So you can think of that in terms of different levels. So like, okay, this is level 1, it's easy, and then level 10 will be harder, and hopefully we'll go from level 1 to level 10, and we'll get better over time. And so those are different buckets you could use. Another kind of bucket would be difficulty levels. So like, okay, we'll have like an easy version, and then we'll have like a medium version, and we'll have a hard version. Or with educational games, we might say, okay, this is going to be for, 5th to 6th grade, and this is going to be 7th to 8th grade, and we'll sort of have that delineation. And that's a very common approach to sort of difficulty balancing and level balancing. So that might look like this. So we have a bunch of people playing our game, and some of them are going to be, in the red bucket or the orange bucket or the yellow bucket. And hopefully if we have enough of these buckets over time, we'll get most of the people kind of in the red bucket, and then we'll kind of get close to that sort of optimal peak. And that obviously, works pretty well. A lot of games are very successful using the bucket method. But this is actually not the reality of the situation. The reality looks more like this, which is for each individual player, there's going to be some perfect sweet spot of challenging but fun that we want to reach. And the bucket method isn't going to work up until the point where we have a unique bucket for each player. But that's hard, and you can't code games using the standard bucket method where everyone gets their own bucket. So now, given that whole problem, we're going to take a little bit of a detour, because obviously this might be a spoiler alert. I know you read the description of the talk, but we're going to take a detour and talk about artificial intelligence, because that's what the talk is about. So what is artificial intelligence? This is kind of, probably people know what this is, but I thought it was important to cover. This is my very bad drawing of a brain. I hope you all like it. It looks kind of like a pink cloud. So artificial intelligence is any sort of computer system that we build that can do things that normally require human intelligence. Obviously, there's quite a lot of debate about what is and isn't AI, and what it does and doesn't require human intelligence, and that is all very interesting, but we're not really going to talk about it. We're going to kick that to the curb, and we're just going to use this as our definition because, again, little rainbow on the computer, very adorable. So that is what we're going to just broadly define as artificial intelligence. And then it turns out that there's kind of two different approaches to artificial intelligence. I'm hoping that this isn't like everyone already knows this, but I don't know. I didn't know this, I do now, but I didn't know this when I was studying it for my master's thesis. So basically the two different approaches for AI broadly can be described as two halves of this question, which is, should we give the computer data or should we give the computer rules? And so I'm going to give you an example. Again, we're all humans in the room, I hope. Humans, everybody? Raise your hand. Okay, good. So we probably all know that this is a cat. Adorable. But computers don't know that it's a cat. And so let's say we're trying to get a computer to say, hey, that's a cat. There's two ways we could do it. The first is we give it knowledge or rules. So cats have pointy ears, cats have long tails, and cute little button noses and 4 paws. And we could give it a bunch of different rules like that and say, okay, if you see pointy ears and a cute nose and a long tail and 4 paws, it's probably a cat. And that sort of approach is basically knowledge-based AI, knowledge representation. This is a very common approach people use in games because games tend to be very limited environments or structures, so it's easy to implement rules for AIs in games using knowledge-based intelligence. So this is one half of AI, is the knowledge-based approach. The other half is data, which says, here's 500,000 pictures of cats. So all of these are cats, and look at all these pictures, and then you figure out for yourself what a cat is based on all these cats that I just gave you. And that is basically, in a nutshell, what machine learning is here's 500 cats, figure out for yourself what a cat is. And that's gonna be what we're gonna talk about today. So I like to think of machine learning as box building, which might sound kind of weird, or maybe it doesn't, I don't know. Which is basically, okay, we have this box, and we're gonna put some data into the box, and something cool is gonna come out. That's what all machine learning kind of boils down to. And there's different kinds of boxes you can build that do different kinds of things. And the box that we're going to talk about, again, spoiler alert if you read the description of the talk, is neural networks, which are really cool. And I'm excited to talk about those. So again, we're kind of detouring. I promise we're going to get back to the thing we talked about at the beginning, but now we're going to sort of give an intro to neural networks. Does anyone have any experience? Does anyone kind of ever knows what neural networks are, kind of how they work? Great, okay. I'm sorry if this is a little low level. I'm hoping to leave time for questions at the end. But for those of you who don't know or have only heard what cool things Google is doing with them, we're going to talk on a very general level about what neural networks actually are. So this is a neural network. I drew this, but this is basically what a neural network is without all of the math, which we can talk about the math at the end, but just to get a good introduction. So this is a neural network. So the way neural networks work is you give it a cat, and then it does some math, and you don't get to really see the sort of math going on, and then out pops a little thing, and this box says, I'm 3% confident this is a cat. I don't know. And then what it does is all these dials you can sort of see kind of adjust based on whether or not it was right about it being a cat. And over time, suddenly, if we give it enough cats enough times, it gets really good at figuring out what a cat is. And obviously, this approach would be really inefficient if you were human, because humans are very slow at looking a lot of pictures of cats. But computers, if you've noticed, are really fast, so they can look at a ton of cats really quickly. So that's sort of why this is a cool thing that a lot of people are doing right now, is because we finally have computers fast enough to do the thing that we'd love to do more than anything, which is just look at pictures of cats all day. So that's, again, obviously there's a lot of math that we can talk about if you're interested at the end, but that's basically how a neural network works, is you give it cats, and then it figures out how to adjust its dials, so it's really, really good at figuring out what a cat is. Which is pretty cool. And obviously, depending on how complex the problem is, you might have more dials, is kind of my metaphor. So figuring out what is or isn't a cat is a simple problem. A lot of problems people are trying to solve are more complicated, so you might need more dials, which would be like bigger and better neural networks. So what we could take from that is that we can make a machine learn anything we want as long as we have enough data, which is pretty cool. I think that's really exciting. Kind of why I got into computer science was sort of this phenomenon, so I think that that's pretty sweet. So now that we've sort of had our detour into what a neural network is, we're going to go back to this question, which is how can we make a game that's just right? I'm gonna now, we're gonna find out about a very cool new game that I've come up with. It's pretty amazing, and how it works is boxes go across the screen and you have to move your mouse to avoid the boxes. And you're doing better at the game if you're avoiding the boxes. I know, crazy game, super complicated, hard to code. I don't know if you'll be able to do it, but that's the game that I've come up with. That's a very easy game. This is also the game that I made for my master's thesis, so if you're wondering how much work I put into the game part of that, you can draw your own conclusions. So this game actually, though, has two important things that a lot of games have, which is there's a measurement of success. So basically there is a mathematical way of figuring out how well you are doing, which is going to be important for this approach that I'm going to be describing to you. So in this case, I'm going to make the measure of success how many blocks have you collided with in the past 30 seconds. If the number's high, you're sucking. If the number's low, you're doing really good. And that is an important thing that for this approach to work, you kind of have to have. The other thing that it has is what I'm calling environment parameters, which is basically just the different numbers that make the game work. So in this case, their blocks could be different sizes, they could be going at different speeds, and we could be spawning blocks at different frequencies. And all of these, by changing them, change the difficulty of the game. Which again, like this simple game has this, but a lot of games have this paradigm, educational or otherwise. So kind of maybe you figured out that the question we're asking ourselves is actually, can we use neural networks or machine learning to somehow control these parameters? Because that would be really cool. Because then they could change the difficulty of the game to get in that sweet spot. So this is how you could do it. So basically you have two different neural networks or two different boxes, and one box, the one up at the top, basically takes in how well you're doing. So I didn't draw that on there actually. That was kind of a fail. But imagine instead of a cat going into there, what's going into it is the current way you're, like how you're playing. Actually, this is all backwards. Let me rewind. Okay. What goes into the first one is going to be, oh, I don't have a mouse, going to be these. So what the environment parameters are currently of the game, and it's going to try and predict your score. So the good news about that is games are constantly updating the score of how you're doing. So this box up here is basically learning to predict what score you have based on the environment parameters of the game. So in this case, you say, okay, right now the guy, whoever's playing, this is the frequency of the blocks, this is the speed, and this is the size. And what I'd like you to do is I'd like you to predict what the score is. And you let that guy go for a while until he gets really, really good at predicting the score of the game. So the measurement of success, how well your player is doing. And then you get a second box, which says, okay, this is how well the player is doing, and I'd like them to actually be having a different score. So I want them to be like doing 50% well. And from that, it will adjust the environment parameters, and it will say, okay, if you want them to be at this difficulty, this score, it would be these environment parameters. That was kind of confusing. I'm not very good at drawing. It's kind of complicated. But that is basically how that works. This is probably the most confusing slide, so we can definitely come back to that with any sort of questions. Actually, I'm curious if anyone has any questions now. Not yet. Okay, we'll warm up. Wait time for you education majors. You guys know about that. We'll get that at the end. But basically, if we can get this two sets of neural networks figuring out how to set the environment parameters of a game to get that difficulty, you can optimize the performance for each individual player. So if each player of your game has an instance of these boxes and they're constantly learning how that unique individual is playing, then it can basically reach that place on the optimal curve for each player. So this is different than boxes because instead of saying, okay, everyone is in this box, or I'm sorry, this bucket, each individual person gets its own little neural network, getting very attuned to exactly how you're playing at that particular moment in time with that particular task. So hopefully that makes sense. This part at the end is kind of the most confusing part. But so that's really cool. And so hopefully now that I have talked about that, you guys can do the thing that everyone's telling you not to do, which is to kick the bucket. Oh, fit the pun in there at the end. So yeah, that is what we'd like to do is, or at least I would like to see in more games, is instead of just sort of these rigid buckets that we're putting people in, we can use machine learning to get very accustomed and individualized to each unique player. So that sort of framework I described at the end is one way to do it, but there's obviously all different kinds of ways to do it, which I'd like to talk about at the end. I'd like to hear everyone else's ideas and stuff. So with that being said, I did say that there are going to be some shameless plugs, which I'll do before the Q&A, just like chat. So a couple things. So maybe you thought I explained that framework at the end very badly, which is probably true. If you thought so, I have a website, katiezaback.com, which has the open source code to an implementation of that framework with a more detailed explanation of how it works. And it is free and open source because it's on GitHub. So if you're a game developer and you're like, I would like to do that in one of my games, it's pretty easy to download and plug it into whatever game you're doing. Right now it works on the web. It launches a EC2 instance and stuff like that. So that's pretty sweet if you're interested in that. If you're not, totally get it. Also, if you are interested in a more in-depth introduction into how to actually code machine learning, like neural networks and stuff like that, I have a free ebook that is literally just a PDF I put on my website, and it is, I've gotten some positive reviews from my mom about it, so not to brag, but that might be something worth checking out if you're interested in more of the math behind those boxes that I showed you, because today I don't know. I don't like learning about math before noon, so I figured we wouldn't do that. Couple other plugs is this was the very first of my sort of endeavor into this initiative that I'm starting, Machine Learning for Everyone. All I have right now is a Twitter, but I'm hoping to build more in-depth educational tools so everyone can learn how machine learning works. Not to get a little political, but I think it's an important tool that a lot of people are using, and you need to know how it works. So that's my plug for that. And then, of course, the last shameless plug is, as I mentioned, I am 1/4 of an indie game company. That's why I'm here. Winsler Games. Our logo is a giraffe, which is pretty cool. We build games that are hoping to build connections between people and talk about important social issues. We just released our first game this past December, so not to brag, but it's available on iOS. Not gonna say where, but Apple Store, gotta do it. And I think Android. But anyway, so those are all my shameless plugs, which I will, of course, leave up the entire time we're talking so you guys can check those out. But now that, unless we need to go back to slides. So that was all kind of fast because I kind of wanted to get through it pretty quickly because I wanted to talk to all of you about what your thoughts are in machine learning and games and neural networks, because I love talking to people about that. And I know that we're all shy and just kind of sitting in different corners of the room, but I am an education major, so I'm not afraid to wait up here until someone asks a question or has a comment. So with that being said, yes.
Hi. So in my experience with neural networks, they take a lot of data to train to become accurate. As a player is playing a game, you might not have all of that data for them because they can only play in real time. Mm-hmm. Do you find that as you tested this out, that you were able to come to quickly bring them to the level of difficulty that you want, or how do you come to this issue of you need a lot of data?
That's actually a really good point and a very interesting question. So what I found is for my very simple game, it was a very small net, so you could do a lot of iterations very quickly. So with that game, I think I ended up giving it 2 environment parameters, which I think was speed and size of the blocks. And because of that, it was a very small neural network, so it runs quickly. So basically, I could increase the sampling speed by quite a bit. When it's running in real time, you basically have to take snapshots. So like at this moment in time, this is what the environment parameters are, and this is how good they're doing. And you're basically feeding that network different snapshots. So that's a very good point where, of course, with all machine learning, you would like to think we just feed it as much data as possible and we kick it into the box and then something cool will come out. But I found with this approach, because it's in real time, like you said, you have to be very thoughtful and sometimes prune back how much information you're giving it, because for each piece of data, basically you're giving the network that increases the complexity of the algorithm running. So basically, smaller networks, you can get more snapshots, which leads to a faster learning time. Another thing that I did not get to do in my thesis that I think would be cool, so if you want to do it, that would be awesome, which is individuals play games multiple times, and so you can have, once you build up the model of how someone's learning, you can sort of access that in subsequent times when they play. So rather than starting from scratch every time, you might say, okay, this is how they were learning or playing the game previously, and we can sort of start with that and then modify as they keep playing. Another thing you might want to do is, I guess this is kind of the bucket approach, but you might say like, okay, it seems like this person is playing like, this person is most similar to these 10 other people who've played, so we're going to start with that network and then individualize it over time. But that's definitely a very good point. Learning in real time is obviously hard.
So if you were to try to generalize it to games with more complex states and larger game spaces, would you try to keep the feature set low so that you could run it iteratively very quickly?
That would be one way of doing it, yeah, is definitely the feature set being very low. Yeah, another thing might be smaller nets that are learning different chunks of the game. So like my game was very simple, right? So like the entire game can be controlled by 3 parameters, but Skyrim is not that. And so you might want to have, similar to how AI works in games now, right? You have different entities that perform different tasks. And so if you chunk those out into different, like, okay, you're going to learn for this specific thing that you're doing in the game, how this player operates, that would be able, then you could sort of parallel process, which would be really cool. But again, the way that this works is obviously like you need some sort of GPU or something to do all that processing, which this was a web game that I built, so that was pretty easy, because I don't know if you've heard of AWS, but that's a thing. So that's what I used. But did that answer your question?
Yes.
Okay, sweet. Anybody else? We got so much time. Yes.
So the machine learning thing is running while the player is playing the game,
Mm-hmm.
and then adjusting it to try to predict. What are you getting out of using a machine learning algorithm that's doing that over? I guess I'm just trying to compare that to like a dynamic difficulty system that is just looking at like player metrics and then kind of using a formula that you've made from testing that isn't like a box that's a machine learning.
Yeah, no, that's a really good point. And I think that's a definitely good question. I don't know if I explained it that well, so I don't know if there's chalk in here. So like,
There's chalk on there if you can look up here.
so like for each wow, this chalk sucks. Okay. Oh, okay, there we go. So like each person might have like some different like function for how well they'll do at the game for different difficulties.
Right.
Okay, so like you could just say, okay, this person is, oh, why do I keep doing that? This person's in box 3, this person's in box 2, and this person's in box 1, but that's if there's only 3 people playing. So the way a neural network is different than buckets is rather than picking a bucket, it figures out exactly what this function looks like. Because, again, like I didn't want to get into math, but basically the way a neural network works is it's a function approximator. So like if the real function looks like this, a neural network might be able to figure out that the function looks something like this. And it gets really close to figuring out what that exact function is for that specific person. Does that make any sense at all? No. Okay.
But his question actually sounds sort of like the data-driven versus rules-based approach that you discussed at the beginning.
Right. Yeah, no, that is very similar. So,
I wasn't specifically talking about buckets, I think.
okay. So, I'm trying to think. Okay, so like, I don't want to get into math is the thing. So the way, okay, so like, we're going to get into math for 2 seconds. So the way you figure out, you define a function is like, okay, let's say this was a 2-dimensional function, there's an x and a y. And you say, okay, every time, x increases by 2, y increases by 1, and we have these different points, and like that's how a function works. Okay, we like know how that works. Okay. So the way a neural network works is it basically like can do this, but like times a billion, if we have a billion of these variables, and it moves them all around until it basically gets a function that looks very similar. Does that make sense? Okay, so the difference between that approach And the knowledge-based approach is, in the knowledge-based approach, we would say, okay, when x equals this and y equals this, that is what the answer is. I don't know if that makes any sense at all. I'm really bad at explaining math on the fly. Does anyone else, maybe you could rephrase the question.
Sure.
Okay.
So if there's a difficulty level, an optimal difficulty level that I want the player to be experiencing,
Right.
and I am figuring out metrics to say like how successful they are,
Right.
and I'm going to code the game to increase the different difficulty variables based on polling the player's metrics and recording that into a database.
So these,
And doing in real time adjustments to those, but without using machine learning.
right.
What's the thing that's different about using machine learning than kind of doing this by hand and doing like the formulas?
Oh, okay. Okay, that was a different question. I thought you were asking a completely different question. Okay, so the difference is if you use machine learning, you don't have to figure out when or how much to adjust these variables. That's what the machine figures out. So the standard game approach is, okay, if they're performing at this level, then I want you to change these variables to equal that instead of what it previously was, or increase them by 2, or so you're defining all of the rules.
Yep.
So that would be, okay, you're totally right that that's what he was asking. I'm glad that I asked you to rephrase. So that would be this. If you have a cute nose and pointy ears and a long tail and 4 paws, you're a cat. And so then act like you're a cat in the game as opposed to a dog. This is, I don't know what a cat looks like, but you need to figure out what it is. And you're gonna do that for me because you're a cool computer. You can figure it out much more quickly than I can with a lot more accuracy than I can. Does that make sense?
Yeah.
Nice, okay. We got there, you guys. Yes, do you have a follow-up question? I hope so, okay.
So, I think in the kind of professional game development community, there's a lot of suspicion of machine learning.
Yes,
Due to the black box nature of it.
yes.
At the moment.
Mm-hmm.
But you make a compelling point about the machine learning being capable of kind of approximating these functions when we don't really know what they look like. Because
Right.
they're very complicated.
Mm-hmm.
But it also seems to me that when you have a function that's very complicated, it's going to take a lot of data, as Josh said.
Mm-hmm.
So how do you kind of mediate between, like, oh, it's simple enough that we don't need machine learning,
Mm-hmm.
versus it's so complicated that we need too much data for machine learning to work on a single individual in a reasonable amount of time? Like, how do you like find that middle ground?
No, that's actually a really good point. Actually, my like full-time job, I work at like it's not important. We work at I work at a simulation center, so we do a lot of like military training games, and a lot of my coworkers are. I'm sort of the dark horse in our community because game AI is very like counter to the machine learning approach in a lot of ways. And I think it's because of that exact point. You're right in that trying to figure out when is a good and not good time to use it is more complicated than I made it seem in this like 20-minute slideshow. I think what I would say to that is, just like with any other form of computer science, you have to be knowledgeable about when is a good time to use different components and to use the components that are best suited to that individual case that are at your disposal. So in the same way that game AI is an art, I think that people don't like to say that machine learning is an art, but it is. There's a lot that comes into play when it comes to, what to give it, how fast is it going to run, how frequently are going to run it, what sorts of, questions are we going to have it answer, not answer. And I guess the thing I will say to you is treat this like you would any other tool in your game developer toolbox. And don't be afraid of it, but also be very thoughtful about how you use it. So like what you were saying earlier, right? Like you have to be thoughtful about how long is this going to take to run or to learn and figure out how you're playing. So like for me in this case, I think that this is a good example of something that has a lot of long-term gain, but not a lot of bang for your buck short-term. So if you're looking to, have an enemy that exists for 5 seconds before you shoot it in the head, it's probably not a good idea to have machine learning try and figure out, you know, how you're going to be moving around and stuff, because it's going to be dead before it even figures out anything cool. But if you're, you know, doing games like educational games in particular, I think are a good use case for this, because educational games are supposed to be about that sort of long-term growth of a player over time. And there's a lot of different functionalities in games, in educational games in particular, that would benefit a lot from the long-term growth you can get from an individualized machine learning approach. But that is definitely a very good point. So definitely not a proceed with caution situation, but definitely be thoughtful about how you're using it. Did you have a question? Yes.
Yeah, I have three.
Oh, okay, cool.
So my first question is, let's say you have a large gamer base, and you find yourself, after analyzing the data, roughly with 3 buckets. Do you anticipate any complementary systems where machine learning or AI will actually analyze that for you and arrive at insights that it can then feed back to you as a game designer to help you understand the game better?
Yes, there's an entire other branch of machine learning that we did not talk about, which is clustering algorithms, which is another really cool thing that you can do as game designers, which is, again, probably you guys already know this, but I never know about math, so I like to talk about math, which is if you have like players and then we're gonna like chunk, this is like their performance over time, it can say, okay, these people are in a group and these people are in a group, and you can say like, okay, we can give all these people probably a thing, and then we'll give these people a different thing, which is buckets, but they're more intuitive buckets because you're not arbitrary. Like, this is gonna be able to look at a lot more dimensions, a lot more different things about your player than you can conceivably just think of when you're coding. So instead of saying, okay, like, this is what grade level they're in, and this is what hair color they have, and this is, you know, like all that kind of stuff, these algorithms can look at massively dimensional data. So you could look at like 20 or 30 things about each individual player and get these clusters, which would be a closer to the individual bucket systems. That's a really good point. Did that answer your question?
It did.
Dope. Okay, you had 2 more, so I'm
Yes.
kind of scared. But
So question number 2 is, how soon do you think machine learning will be used for selfish purposes, such as maximizing addiction for microtransactions?
I mean, it's probably already happening. That's actually not related at all to this talk, but one of the reasons I like talking to people about machine learning and educating people about machine learning is my friends get irritated because I talk about it all the time, but increasingly it's being used for nefarious purposes or exploitive purposes, and I think it's very important, being a person in the 21st century, to know how these algorithms work and you know, what they can do and what they can't do and how they might be being used for you or against you. And that's what, again, shameless plug, like that's kind of what my endeavor going forward is creating educational content for people so they can understand how it works. Because the other thing, if you get anything out of this talk, I know I didn't do a very good job of explaining it, but it's not as intimidating as you might think it is. It's very easy to implement these algorithms. They're not as complicated to understand as you think. That's kind of why I use the very basic box strategy. Is if you could understand there's a box and there's different dials and you're turning them, you basically understand more than 90% of the people who read anything about machine learning. So I don't know if that answered your question, but it did give me a chance to go on my diatribe, so happy about that. And then you had one more?
Yes.
Okay.
Chihuahua or muffin?
Chihuahua or muffin? I don't know what that means, but I'm like muffin every day. I don't, and only the top part. I don't know
There's
what
an
that means.
interesting, I guess it's meme status now about how.
Oh no, I have seen that with the little blueberry muffin.
Yeah.
God, I love that. Every time that goes around Twitter. Have you guys seen this? It's a thing where like it makes like blueberry muffins look enough like chihuahuas that it tricks like neural nets and thinking it's frogs. See, this is why machine learning is more an art than people think. That's also why you have to be thoughtful about what data you're giving your algorithm, because if you're only giving it really obvious pictures of chihuahuas and you're not giving it blueberry muffins, it's going to get tripped up. Yes.
Hi. So
Hello.
I have 2 questions.
Great.
One's
Okay.
very nuts and bolts, and the other one's very meta.
Okay.
So I'm gonna ask the nuts and bolts one first.
Great.
Save the meta one for later.
Yes.
So I teach middle school students to create
Amazing.
games, and I'm interested in applying machine learning techniques. in
Yes.
So what I'm wondering is the algorithms and coding and so forth
Mhm.
that you and other people
Mhm.
have or already pioneered.
Mm-hmm.
How accessible is that to a audience or to developers who have, some basic programming and coding skills?
Yes.
And not very advanced.
I love that question. Okay, so I'm going to tell you two things. The first is very accessible, because here's the truth that no one wants to say. Everyone hates implementing these. Everyone wants an easy-to-use library where you don't have to implement anything and you just go make neural network and then it does all of your magic for you. So the other thing I will say is you should go to my website and you should download the ebook. And that outlines how to implement okay, so like the classic machine learning problem is, here's a handwritten letter, what letter is it? That's sort of like the MNIST data set, that's sort of like the benchmark, and it talks about how to implement a very simple classifier using a library which is kind of now not defunct, but it's not like the popular one, but this is the library that it uses, Keras. It is so easy, it's like 5 lines of code. And you can have it, you can download the data set, you can implement a neural network in 5 lines of code, and you can get it to run and accurately predict handwriting. And when I did that, I probably lost my mind. I was so excited. So even if you don't use my ebook or whatever, if you manage to get some middle schoolers to have a Keras image classifier, please email me about that, because I want to hear about it. Because if I was able to do that when I was in middle school, I'd probably I would freak out. It's so cool. So that is what I'd say. It is not that hard. There's obviously a lot of customizing and things you can do, but TensorFlow would be the other big library. Everyone's incentivized to make it easy to implement these, because especially businesses, there's big dollars to be gained from having a lot of people being able to implement this stuff. So please have your middle schoolers make a handwriting classifier and then tell me about it, because that'll be so cool. My mom's a middle school science teacher, so that was also what I maybe thought I was going to do in a former life before I found out about computer science. So anyway, yes, did that answer your question? Nice, okay. And then you had another one? Okay.
I'd like to give someone else a chance.
I think, does anyone, yes.
So yeah, more of a, I guess, theory question, but you were saying that when you implement your algorithms, you basically are, a priori setting, an accuracy level that you want your player to have, or a performance level, you want them to, be 50% accurate, or, I'm just simplifying for the sake of example, but if what you want to optimize is engagement, how do you know what would be the level to set in order for the player to be having fun versus just
That's a good point. Okay, so and I that's a good question, because I don't think I explained that well, because I don't know, I got to the end of the slide deck and I was like, oh shoot, I'm gonna run out of time. So I don't think I explained that well. So what I think you're describing is the measurement of success needs to be I don't know how this is obvious, but it needs to be what you want it to be. I know that doesn't make any sense, but if your measurement of success, it's going to optimize for that. So if your measurement of success sucks, then it's going to be optimizing for a bad game. So basically you could think of it as the measurement of fun. So I'm trying to think of what a bad measurement of success would be. So if I don't know. Can anyone else come up with an example? I'm trying to encapsulate it.
I think just to understand the question, it's how do you use this approach if your measure of success isn't something that you can understand from the game, like it isn't a game metric or a statistic? Right?
Oh, okay. Oh, that's a completely different question. Okay, that's actually very interesting. So, you can't. So that's an easy question. So if you can't, machine learning works by numbers in, numbers out. So you couldn't.
My question was, would you do a more kind of behavioral kind of test to figure out most people are happy when the difficulty level is set at 50% accuracy, or that might also tell you that some people like to be 50% accurate and they're having fun in that really challenging state, but some people will give up unless they're at 90%.
Oh, okay, yeah. No, so that's also a good point. So not to get all numbers, but most things in life are quantifiable by some means.
Yeah.
It's just not going to be a perfect comparison. So you cannot quantify fun, but you can quantify how many blocks did you hit. And if you're hitting 500,000, that sucks, right? So you have to use you've kind of already answered your own question.
Yeah, or
Is-
I guess you could also use if people were playing the game voluntarily, you could see when they give up. Like
Right,
oh,
yeah, no.
yeah.
Yeah, there's all kinds of different metrics you could use that you're sort of trying to figure out and predict when a player is going to hit certain points on that metric. That's a really good point, actually. Yeah, is if you're trying to do something that's not quantifiable, don't do this. Or if you do, you have to find out a way to make it quantifiable, because computers don't like feelings,
Yeah.
not to insult them. But yes,
Yeah.
you have your hand up very high in the back.
Yeah, so I mean, I guess part of it was to kind of join this discussion,
Mhm.
admittedly. Like, my thoughts on that is, like, if you want to quantify, like, improvement in score, it might require data beyond just from the test. So, like, maybe have your sessions tracked by student, for example, and the teacher would have to be like, oh, this is their score before and their score after, and then perhaps from, like, before doing the session, the game session, and then after doing several sessions or something like that, and then maybe, like, hypothetically, they could take that data of, like, oh, what had the most improvement for, like, from a low score to a high score
Mm-hmm.
from after doing that in order to truly comprehend, and maybe that would also help encourage, oh, this is the right way for them to learn how to learn, so this is the way that I'll try to adopt the approach.
Yeah, no, that's definitely a really good point, is these things can save state for multiple sessions and things like that.
Mm-hmm.
You have had your hand up for a while, yes.
Yeah, just to connect a couple things with some examples and see what you think of them.
Cool, yes,
the
I
things
love that.
came up that I've seen are so my impression of machine learning's accuracy is driven by like 3 examples that I've seen or heard about.
Yes, is one of them the muffin chihuahua example?
One of them is Google Photos
Mm-hmm.
being able to type in a filter and it being able to try to see if it can understand that.
Yeah,
And is almost exactly your example, which is cat.
yes.
If I type in cat, I get about 100 pictures of my dog. Out
Yes.
of about 5,000. But it's just decided those 100 pictures are of a cat, not a dog. So that doesn't give me a lot of hope.
Well, they're similar, right? Well, it's gone now, but they both have tails, and some of them have pointy ears. It's hard.
But at the same
Oh,
time, I've
those are
also
gone.
heard recently of 2 different things using machine learning for
Mhm.
video games, which is one, there was something about, I think it was Dota, somebody making an AI that can beat all of the best players.
Yes, this is a big thing, yes, in the gaming community. Ooh, people have opinions about AIs that can play, like, Go and stuff like that. This is like a
And
thing.
then the other one was actually to analyze churn for an MMO.
Mhm.
They had something that was analyzing when players are going to never play again.
Mm-hmm.
And
Yeah,
then
yeah.
sending out an email
Come back.
to say like, hey, come back, here's some free stuff.
Yeah, I love that.
Talking about how, well, yeah, it was using machine learning, so we don't actually know what it is. We
Mhm.
can't actually tell what those metrics are,
Mm-hmm.
but we can employ it and seemingly keep some more players.
Yeah, no,
And
those
it's
are
just
actually
something
all
else for us.
really good examples. That actually touches on
It's
a,
useful.
yes, that touches on a big, if you're gonna have anything other than you can, well, this is just all of my, being a shameless person, but like, if there's another thing you take from this talk beyond, this is definitely something you can figure out and implement. The other thing I will say is start with small, like projects or goals, like for your machine to learn, not like I'm gonna build, like start with easily, like tiny little chunks, like for Google being like any picture of any cat versus any dog versus anything else, that's huge. That's a really hard problem to solve, and like Google could probably figure it out because they're Google, but like us, us indie devs just like doing whatever, like that's not gonna be anything we can solve. But something like that, with the blocks and they move, that's a very small chunk. So if you're going to be wanting, like if you want to sort of jumpstart putting any sort of machine learning into your games, definitely my number one piece of advice is to start with a very small, reasonable, easily defined thing that your algorithm can learn. Think of it as like, we're going to start by teaching a kindergartner how to like tie its shoes. We need to make, well, that's actually kind of hard, but like we need to make this as easy as possible and as easily defined as possible. We want the data set to be easy to get, and we want the like training set and how accurate it is to be as easy as possible for us to figure out, because it's going to make it so much easier for you guys to get your algorithms running. Spoken from experience. Anyway, so that is a very good point. I love that, especially with the email thing. That's like a tricky little, I'm sure that's how I get so many spam emails from like Staples and stuff. Anyway, I think you had one more question that we will use to wrap up the session. Yes?
Sure, so my meta question has to do with transfer, and that's actually more of amusing,
Mm-hmm.
like thinking about stuff. So
Like style transfer and stuff like that?
No, actually,
Oh.
so there's different levels of transfer. So one is what you were kind of getting at, which is how performance in a game can be correlated with deeper learning comprehension and
Oh,
performance
yeah,
that,
okay.
is gauged in other contexts.
Mm-hmm.
And then there's also the transfer of performance in one educational game versus another one,
Yes.
and how that process can be coordinated in some fashion,
Mhm.
so that gets to the problem of time versus data.
Mm-hmm.
That in any particular gameplay experience, you might not have very much time to accumulate data to train
Yes.
your net.
Mm-hmm.
But maybe you can leverage data in machine learning that has come in previous experience with the same player.
Mm-hmm.
And so how can you provide a framework to help the implementers and the practitioners, the teachers and so forth, use that?
Yeah, no, that's such a great question. And that's definitely something that, again, machine learning, we're not great at yet, is this idea of, okay, I built this thing that does this very specific thing. Can it do this other thing that's similar? Like Chihuahua versus Muffin. Like, sometimes things that you'd think would easily transfer from one to another don't. And definitely the number one thing I'll say to that too is think about what you are giving your algorithm and what you aren't giving your algorithm. That's a big, big thing. And I definitely love the idea of different chunks all sort of coming together and building kind of a more holistic perspective on a student or a player. I think that's such a cool idea. This is all, I know it seems like it's been around for maybe a bit, but this is also very much in its infancy, and there's tons of cool things to be built, and I hope that you all help us all build them, because that would be so cool. And I guess to kind of wrap up, the other thing I'll say is, if anybody wants, has more questions about this talk, or is, you get home and you're wanting to implement an algorithm or something and you're stuck and you can't find resources, or you're musing about something, literally shoot me an email, because this is like my side job of just talking to people about this stuff. So I would love it if you came to me with questions or thoughts, or you need, resources, or you're implementing something in your game and you have, you're wanting to talk about it with someone, any of that. Shoot me an email, it's on my website, and that would make me over the moon. So, with that, it is 12:01, so I'm 1 minute over, but thank you so much for coming to this talk. I didn't think anyone was going to come, so I'm really happy about that. Thank you so much. Yay.